what I'm going to do is turn on the DART system and the mass spectrometer. Then I'm going to go ahead and measure a tablet and determine the elemental composition and the probable identity of the compounds in the tablet. So we'll begin by just double-clicking on the DART controller to turn on the DART power supply. We'll see the DART tune bar and switch from the off mode to the on mode. The DART system comes up in standby mode, so we'll click on the little leaning man icon and switch him over to run. If we want to see what's actually going on, there is a parameter page here that shows you the current condition of the DART system. The glow discharge needle is on, the grid voltages are on, the DART gas heater is warming up to temperature, and helium is flowing. While that's happening, I'll go ahead and start up the mass spectrometer. And we'll wait for the program to start up. If the mass spectrometer has previously been tuned, there will only be two parameters that have any effect on the measured data. We'll take a look at those in just a second. Program comes up with the main window. What we really want is the instrument control window, so I'm clicking on the little icon for the mass spectrometer to call up the mass spectrometer tune window. As soon as that opens up, we'll see parameter pages for the mass spec. The instrument comes up in a standby or warm-up condition. We're going to switch it to operate mode, and you begin to see peaks right away over here. So this is the background. It's fairly low intensity, but we see the instrument operating. The only two parameters that are relevant on a day-to-day basis are this RF ion guide voltage called the peaks voltage, and that determines the lowest mass that you see in the mass spectrometer. If you just take that voltage and divide by 10, that'll give you the approximate lowest mass you see. For example, here we have it set to 600 volts, and if you divide by 10, we're seeing about mass 60 and higher. If I set it to a lower value, you'll actually see the atmospheric background peaks down here. For example, this is a typical DART background where mostly what you see is water dimer at mass 37. Water is 18, so 2 times 18 plus 1 is 37. That tells me that everything's working very nicely, so we'll go back to the other condition. The only other parameter is the orifice voltage, which defines how much fragmentation we see in the spectrum, and Bob will be talking about that a little later. Okay, I'm going to go ahead and set up a spectrum acquisition here. So we'll start up the acquisition, and all we really need to do here is to specify the name of the file. Let's just call it unknown tablet, and put a 1 after it in case we got the caps lock key on. And we'll save it in a folder with today's date. Okay, the rest of the pages are optional, but we're going to just collect data from M/Z 60 up to about 700. The machine will run for minutes unless I hit the stop button, and we'll save spectra about once a second. We can go as fast as 10 spectra per second, but we aren't going to gain much for this analysis. And then we'll hit the finish button. I created a new folder for today's data, so it's reminding me that we need to create that folder. Now, I'm going to have it show us a real-time spectrum acquisition and a real-time chromatogram or time profile for the ion current. So the program is going to open up both of those windows, and we'll wait for the start button. As soon as the start button shows, we'll begin collecting data. Okay, from right about here? Okay, we're going to open up a file to save the data, and so we'll acquire, start acquisition. We'll get a little wizard that asks a lot of questions, but the only thing that's really important here is just the name of the file. We'll call it unknown tablet A, and we'll save this in a folder with today's date. There are some other parameters we can look at if we want to, but essentially just to review, we're going to collect data from mass 60 up to mass 700. We'll set the program to run for 10 minutes unless we press the stop button before that. And we'll acquire spectra once every second. You can go as fast as 10 spectra per second, but for DART applications, this is usually good enough. So we'll hit the Finish button. The program will open up a data file, and we'll wait for the Start button to appear. As soon as the Start button appears, we can begin collecting data. Now, once I hit the Start button, I'm going to reach over and grab the tablet with some forceps and hold it in front of the DART. And then I'm going to wave some reference compounds, some polyethylene glycol 600 in front of the DART. So here's our Start button. We'll let it run for just a second or two to collect some background. Okay, and I'll go over and grab the tablet with some forceps. If this were a real sample, of course I should be wearing gloves, but I'm going to skip that for a moment here. Okay, now we're just going to wave this tablet to the DART. We want the gas to graze the surface of the sample, but we don't really want to block the gas flow into the mass spectrometer orifice. And so you see several peaks appearing on the top. I'll do that again. We're holding the tablet in front of the DART gas stream, but just letting the sample graze the tablet like that without blocking the orifice. I'm waving the tablet around in front of the sample, but I mean in front of the DART. Okay. And you can see when we take the tablet away that the signal is going to disappear. Okay. And we'll be back to background. Now we'll go ahead and set that down, and we'll pick up some polyethylene glycol on a melting point tube. This is undiluted polyethylene glycol, and that's just going to show how much contamination we can put in front of the system and still have it recover when we take the sample away. Okay, so that's gone. Now we're done. We're back to baseline levels. We'll go ahead and stop the analysis by pressing the red stop button. And we'll set the DART back to standby mode. That just leaves everything heated up and purging with nitrogen, but it shuts off the helium and the high voltages to just to conserve helium and set things into a mode that's ready to go again. Oh, sure. You won't see any signal while I'm doing that, but at least you can see me.
Yeah, just for action.
Well, actually, I guess I can. Okay. So just like that. Just okay. All right. Now what we'll do is open up a program to view the data. Let's close one of these so we can get to the desktop. Okay, we're going to open up the TSS Pro program to process the data. So we'll run the data reduction program. We'll translate an AccuTOF file, which will be in this one, in this directory. This is just showing us a little time profile for the ion current, just to let us review this and make sure we're looking at the file that we want to look at. Click the Open button, give it an initial calibration to import the data. Just accept the defaults. And now the program has actually found the reference compound, locked in on it, calibrated the file, and now all of the masses will be exact. That probably went by very fast, but in short, what it did was find this polyethylene glycol spectrum. We know the exact masses for each of these reference peaks, so the software finds those. Curve fits the time versus mass profile. If the curve fit is good enough and the fit is within certain tolerances that we specify, it just automatically saves that in the data file. So anything I look at here is going to be correctly calibrated. For example, we take a look at this average mass spectrum. We measured the tablet 3 times. Here's an average mass spectrum for the tablet. We see 3 different peaks in here. These have all been properly calibrated, so what we're going to do is save this to a file. I've got this set to save up to a clipboard right now, so let's save it to a file instead. And so we'll save the mass spectrum in a folder where we can find it later. Let's just save this in the workshop folder. Now we'll open up a program that lets us figure out what these peaks mean. Elemental composition program. We can just open up the data file we just saved, which is going to be the last file saved. Now, let's start with the 152 peak here. We'll calculate some possible elemental compositions for this thing. What we're doing then is taking the measured exact mass to, the mass is accurate to 3 to 4 decimal places. We're just assuming that it might just have carbon, hydrogen, nitrogen, and oxygen in it, and asking the program to tell us what possible combinations of those atoms give us a match that matches exactly within 0.005 mass units. We get 3 possible compositions. We don't know which one's right, so we're going to match the isotope peaks as well. Not just this peak at 152, but the carbon-13 peak at 153, and so on. The computer generates a theoretical profile for each of these proposed compositions and then matches that to the measured data and tells you which one is the best match. The best match shows up on top. So the software found 3 isotope peaks with an average 1 millimass unit error. The abundances match within 0.02%, and you wind up with a score that the smallest score is the best match. So let's see if there's anything in the database that matches this formula. DART produces an M plus H plus in positive ion mode, so we're going to subtract an H and search the NIST library database to see what compounds show up. Okay, the program searches the NIST database, and the most likely candidate turns out to be acetaminophen, or Tylenol. And here's the structure for the compound. This is not guaranteed to be the structure as we look at fragmentation, but it's the most likely candidate because it has the most synonyms and it's found in the most databases. Okay, let's take a look at another peak and see if we can identify what that is. 316 peak right here, and we'll calculate the possible formulas for that. Just hit the button. We get 5 possible compositions. Which one's right? Well, let's do an isotope match. The best match turns out to be this top one again. Let's see if there's anything in the library that matches that. We'll subtract an H and search. And the best match turns out to be an oxycodone. So here we've identified an acetaminophen and oxycodone in the tablet, or at least we've proposed assignments for those. Those are likely compounds to be found in the tablet, so that's quite reasonable. So now we've treated both of those measured masses as unknowns, and we've identified their elemental compositions and proposed candidate compounds. Another possible way to do this is assume that we're looking for drugs and search a program that would label any compounds found from a list if they're found in a given sample. So we'll take the same spectrum we just measured and look at it in a different program, and then we'll take a list of drugs right here, probably several hundred drugs and their elemental compositions saved in an Excel spreadsheet here. As soon as the program finishes loading the drug list, we'll ask it to go through the mass spectrum and just name what it finds. Okay. Again, DART stores an M plus H plus in positive ion mode, so we'll ask the program to go through that list of drugs and add an H to each of their compositions and search the program and tell us what it finds. And there we go. Now from the drug list, the program found 2 peaks. First one is the acetaminophen at 100%, and the other one is an oxycodone at mass 316. And they're both within the error tolerance that we expected. The question is, what's this 303 peak? Well, it's probably a dimer. Let's have the program search for dimers. And sure enough, it turns out to be a dimer of acetaminophen. Let's do that again, and let's have it label what it's finding this time. So first we'll search, and we find acetaminophen and oxycodone plus H, and then we'll have it search for dimers, and the 303 peak turns out to be 2 acetaminophen plus H. So we've identified all the major compounds in the tablet without knowing anything other than their exact masses and the isotopic information in the spectrum. That's probably it for the first segment.